Hey guys, today we're going to be seeing what are complex numbers part 1, and in this series I'm just going to be talking about complex numbers, some things you can do with complex numbers, but I'm planning around 6 or 7 videos in this complex numbers series, and you're currently in part 1. And in part 1 we're going to be talking about what are complex numbers. Okay, so here we have a simple little chart which is labeled complex number, and complex number contains real numbers and imaginary numbers, and we're going to get to that. But first we need to see how a complex number is represented, right? So one of the main concepts would be that you have to know that an imaginary number, in this case I, is equal to square root -1. And I is a actual imaginary number. You can't just say, okay, assuming z is equal to square root -1. No, this value is square root -1. So if we square both sides, that's saying, okay, I squared is equal to square root -1 squared, which is just -1 because the square root and the square cancels out. So we have I is equal to square root -1, and I squared is equal to -1. Now let's try I cubed. Well, we know that I cubed is simply I squared times I. We know that I squared is -1. And we know that I is just simply I, so I cubed is -I. Now, what's I to the power of 4? Well, once again, I to the power of 4 is I squared times I squared. I squared from over here, we see that's -1 times -1 is equal to 1. So I to the power of 4 is equal to 1. Alright, so we have these rules out of the way, and you do need to memorize them because they do come up in a lot of complex number problems, and they will allow you to actually interpret what the problem is asking you to find. But like we have I squared, I cubed, and I to the power of 4, in addition we also have their inverses. We have I to the power of -1, and that is basically 1 over I. If we multiply both the numerator and denominator by I, we get I over I squared. From over here, we know that I squared is -1, so that's basically I over -1, which is just -I. So I to the power of -1 is -I. Next, let's find I to the power of -2. I to the power of -2 is 1 over I squared. We know that I squared is just -1. 1 over -1 is -1. So I to the power of -2 is -1. Next, we have I to the power of -3. This can also be written as I to the power 1 over I to the power of 3. And you can multiply this by I over I. We get I at the top, and we get I to the power 4 at the bottom. We know that I to the power 4 from over here is 1. So I over 1 is just I. Next, let's find I to the power of -4. Once again, same thing. I to the power of -4 is 1 over I to the power of 4. And we know that I to the power of 4 directly from over here is 1. So we can say 1 over 1, which is just 1. Alright, since we now know a little bit about this imaginary number, let's start to solve some problems. The first problem is, what is I to the power of 7? So we know that I to the power of 7 can be rewritten as I to the power of 4 times I to the power of 3. And the reason why I did this is because, as you can see, we have I to the power of 4 and I to the power of 3. That looks familiar, right? If we go up here, we see that, oh, okay, there's the I to the power of 4 and a I to the power of 3. We know I to the power of 4 is 1, so we're just going to say 1. And we know that I to the power of 3 is, well, that's just -I. So we're going to do times -I, which is -I. So I to the power of 7 is equal to -I. Simple enough, right? Well, if you have a bigger problem, such as over here, I to the power of 19, which isn't really that big, but it would be tedious trying to split everything into 4s and then trying to find the what's remaining. And yeah, it's just a lot of work, especially when we get to other problems, which this 19 may be, I don't know, like 257 or like 1043 or something like that. We don't want to just split it up into I to the power 4 and I to the power 3 or I squared, right? So there's actually an easier situation. From here, I was trying to make an I to the power 4, as many I to the power of 4s as I could, because I to the power 4 is an easy value to remember, right? It's just 1. And then whatever I have remaining, that would be over here. So 7 minus 4 is 3, right? And we see that I cubed is negative I. And oh, look at that. Our answer is also negative I. Meaning that our answer was also I cubed, right? Because after all, I cubed is equal to negative I. So what I did over here, I divided 7 divided by 4. And that's 1 with the remainder of 3. Now, we take this remainder and we do I to the power of that remainder. And I to the power of 3 is negative I, which is how I got this negative I as our answer. So if you want a more formal way of putting it, you could say that, okay, if you have perhaps I to the power of, I don't know, Q, and you're asked to evaluate it, then you would do Q divided by 4, and then you would get some quotient, you would get like something here, and then the remainder, let's say it would be n. The remainder is n. N is the remainder. Then your answer will be I to the power of n. That would be your answer. And the reason is because this I to the power of 4 is just 1. And 1 times anything is basically that thing, right? Which is why we're just saying, okay, it's I to the power of n, where n is the remainder, once again. Now let's try it over here. It may seem a little confusing, but I promise, it's not that hard. Let's apply this formula over here. So that's basically saying that we first need to divide this 19 by 4. 19 divided by 4, that's 4, with the remainder of 3. Now we do I to the power of that remainder. The remainder here is 3, so I to the power of 3 is negative I. So this too, I to the power negative 19 is also equal to negative I. Alright, so the basic, I don't know how you want to call it, the basic formula to find I to the power of anything is this. So in order to find I to the power of n for when n is greater than 4, the reason I did when n is greater than 4 is because we already know when n is equal to 1, this is a 1, when it's equal to 1, 2, 3, and 4. So we technically know that. It's going to be harder when we have, like, for example, I to the power of 257, which is greater than 4. So when it's n is greater than 4, divide n by 4 and let the remainder be r. The answer will be I to the power of r. So let's apply this to this problem. Over here we see that we first need to divide n by 4. N over here is 257. So let's divide 257 by 4. So this is just going to be 6, 24, 1, 17, 4, and the remainder is 1. And let the remainder be r. So r is 1. The answer will be I to the power of r. We know that r is 1, and we know I to the power of 1 is simply I. So I to the power of 257 is equal to I. And yeah, this problem wasn't too hard once you actually know basically how this works. Then you're set to solve any other problem. In fact, let's try another problem. Let's take I to the power 407. Once again, you divide n, which is 407, by 4. So 407 divided by 4, which is 1, 0, 1, and remainder is 3. Then our answer is I to the power of r. R here is 3, so we get I cubed, which up here we saw is equal to negative I. Is equal to negative I. So therefore, I to the power of 407 is equal to negative I. Alright, we can do the same thing for negative numbers. So we see that n is equal to negative 723, so n is equal to negative 723. But instead of saying n is equal to negative 723, it is though when we follow this rule over here, this I to the power negative 723 can also be rewritten as 1 over I to the power 723, right? It's the same exact thing. Now, let's just find the value of this. So here, n would be 723. 723 divided by 4. 180 and the remainder is 3. So then it would be I to the power of 3. And what is I to the power of 3 equal to? Well, I to the power of 3 is simply negative I. So we get 1 over negative I, which is negative 1 over I. Negative 1 over I, which is negative I to the power negative 1. A lot of negatives here. And from above, we know that negative I to the power of negative 1, if we go here, I to the power of negative 1 is negative I. So we could say that minus this is equal to negative I, and overall this is equal to I. So these negative exponents are a little bit trickier than simply like positive exponents such as this one, but overall it's the same procedure. Just convert it into this form, apply this rule over here, and then just simply simplify it with the rules above. So this I to the power negative 723 would be equal to I. Alright, so hopefully you got a gist of that, and now if you want you can try these 3 problems. Actually, I encourage you to try these 3 problems. They're basically the same thing what we talked about, but if you do them on your own you'll get sort of the hang of it. I could like make videos all day and then you guys could see me like say the solution out loud, but I don't think it would help. You guys actually need to solve it. So just try to solve this, and yeah. Alright, so let's start off with this one. This one we did questions like this previously, so once again, same thing. This is n. We do n divided by 4. So 135 divided by 4, which is 3, and that's 12, 1, 15, also 3, 12, 3, and the remainder is 3. Then our answer will be I to the power of that remainder. So I to the power of 3. I to the power of 3 from above over here. I to the power of 3 is equal to negative I. So our answer for this one will be negative I. There you go. Now, for this one. This one, I think you may have noticed, is in the denominator, right? So that has to do something with negative exponents. So, but nonetheless, the procedure is exactly the same. We see n here is 58. 58 divided by 4, which will be 14 remainder 2. The answer would be I to the power of the remainder, and we know the remainder is 2. So I squared is negative 1. So 1 over I to the power of 58 is equal to negative 1. And how did I get this? Well, technically I ate up a step, but I hope you knew that. Over here, if we take this here, we solved this part, and this part is this whole thing. So negative 1 is actually the denominator. But if we rewrite it, we get 1 over negative 1, which is equal to negative 1. So in this scenario, this negative 1 and negative 1 are the same. But for example, if you had like something like negative I over here and you said the answer was negative I, that would be incorrect. So make sure you always know what you're solving for. In our example, we solved for the denominator, but the denominator was just not the whole entire question. We also had the numerator to consider. So just make sure you know the whole problem. But either way, our answer is 1 over I to the power 58 is equal to negative I. Alright, and this last problem. This last problem may look a little tricky, but I promise you it's not that hard. So we know that from up here, we see that negative square root 1 is equal to I, just I to the power of 1. So whatever is in here, that's basically negative I, right? To the power of 4n plus 3. Now, judging by this 4n plus 3, well, we know that I to the power of remainder would be our answer, right? And we have 4n plus 3. So 4n, it automatically should kind of click something in your head. 4n, we can disregard that because you know that I to the power of any multiple of 4n will be 1, right? Because we know I to the power of 4 is 1. I to the power 8 is also going to be 1, so we can disregard that. It's just going to be 1. Now we have this. This represents the remainder. So 3 would be the remainder. And we know that in order to find our answer, it would be I to the power of this remainder, this 3. But here we have negative I. So another way we could write this would be, let me just take this away. It would be negative I to the power of 4n times negative I to the power of 3. This is simply just going to be equal to 1. 1 because we saw that negative I or any I to the power of any multiple of 4 is just going to be 1 times negative I to the power of 3. Well, we know that this, let's just rewrite that as 1. Negative I to the power of 3 is still going to have that negative. So that's negative I cubed. We can disregard the 1. So negative I cubed. We know that I cubed is equal to negative I. So negative I cubed would be equal to simply I. Alright, so that was the quick intro to these imaginary numbers. But we haven't really gotten to the complex number part of these imaginary numbers. We know that these imaginary numbers do come into play in complex numbers. So let's jump into the complex number part. Alright, so a complex number will always be in this form. And you probably see why we need to learn about all those I and imaginary numbers is because a complex number actually has an I right there. So you know that this I isn't like a variable or anything. It's an actual number. It represents square root negative 1. I represents square root of negative 1. And here, A and B are real numbers. So let's take a few examples of what could be complex numbers. Well, one example of a complex number could be Z is equal to, I don't know, maybe 7 plus 4i. Well, 7 and 4 are both real numbers, and it's in this form. That's a complex number. Another complex number could be Z. I apologize if this looks like a 2, but it's a Z. Maybe it's equal to negative 14 minus 1073i. That's still a complex number. It is in this form. So essentially, any number in this form is a complex number. So now that we got those complex numbers out of the way, it raises maybe like an important question saying that are all real numbers complex numbers? Well, let's see. Let's say that maybe B was equal to 0. That would be Z is equal to 3 plus 0i, and Z is just equal to 3. Well, 3 is a real number. This 0i is still there, but because of this B equals 0, it just disappears. It just becomes 0. So, hence, we could say that all real numbers are complex numbers. They're all in this form where B is equal to 0. But that's not that important. It is a good thing to keep in mind, but we'll move on to a bit trickier problems in a moment. So before we go on, furthermore, if someone says that, okay, find this, what is that equal to? Well, that's basically saying what is the imaginary part of Z. And if someone says this, they're saying what is the real part of Z. So, this is our complex number. The real part will always be this part, and the imaginary part will always be this part. So this imaginary part is a real number that is always multiplied with I. And the real number is just a real number which is by itself. So in this scenario, the imaginary number would be b, and the real number would be a. But if we had another question, say z is equal to -7 minus 4i, what would be the imaginary number of z and real part of z? Well, same thing. The imaginary part of z is the number that is multiplied by I. So it won't just be 4, it would be -4. Because remember, a complex number is in this form, z equals a plus bi. So here the imaginary part of z would be -4, not just 4. And the real part of z would be this part, -7. Let's try a few more problems, or maybe one more problem, since it's not really a hard concept. It's just to familiarize yourself with the imaginary part and the real part of a complex number. So if we have another complex number, let's say z equals 1043 minus 7963 I, what is the imaginary part of z and the real part of z? Imaginary part will always be the part that's multiplied with I, so that's -7,963, and the real part will always be the other number, 1043. In addition, if the imaginary part of a complex number is 0, then the complex number is purely real. An example of this would be z is equal to 3 plus 0i, which we saw earlier. We know that the imaginary part of z is equal to 0, so this complex number is purely real, because it has no imaginary part. The opposite is also true. If the real part of a complex number is 0, then the complex number is purely imaginary. So that's z is equal to 0 plus 7i. The real part is 0, so all we have is the imaginary part. Z is equal to 7i. So this is purely real and this is purely imaginary. Nothing too revolutionary, I guess. It's just how we view complex numbers, and over here we updated this kind of chart thing. That's saying z is equal to a plus b, where a and b are real numbers, a is the real part, and b is the imaginary part. Something to not get confused is that in the imaginary part, I is not included. Instead, the imaginary part is only the number part. I is not included in the imaginary part. Alright, so wrapping it up, that was complex numbers part 1, what are complex numbers. In this video, hopefully you learned how to evaluate different values of maybe I to the power of 77, I to the power of -46, things like that. And you also learned the actual format of a complex number, which is z is equal to a plus bi, where a and b are real numbers. And you learned about purely real complex numbers and purely imaginary complex numbers. And we got a first-hand glimpse of what complex numbers, what they actually look like. And we have some examples here. 10 plus 4i, we have minus pi minus 64i, 3 minus I, and 69 plus square root of -69. And this one is a little bit different. It doesn't have an I in that, yes. But we will get to that in part 2 of this series. So yeah, thank you for watching, and if you want to learn more about complex numbers and the different rules you have with complex numbers, because honestly guys, there are so many things you can do with complex numbers, make sure to check part 2 and on for those. Okay, thank you, bye.